everyone, our project is about person identification with smartwatch. When it comes to person identification, what will come to your mind? Face, iris, or fingerprint recognition? No. Some of them are not enough to protect your privacy. In addition, your smartwatch might not have a camera for face or iris recognition. Neither could it read your fingerprint. So, how to realize person identification in your smartwatch? The answer is ECG and PPG. That is because nowadays, most of the smartwatch have been equipped with ECG and PPG sensors. For example, Apple Watch, Huawei Watch, Samsung Galaxy Watch, and so on. According to Wikipedia, ECG records the electrical activity of the heart using electrodes placed on the skin, while PPG is an optical tag that can be used to detect blood volume changes. The traditional way to collect an ECG signal needs hospital settings. For PPG, researchers usually prefer to collect it from fingertip, where have more blood vessels. In our project, we collect ECG from chest using Polar H10 and PPG from a smartwatch named GroupCheck. With wrist-based PPG, person identification could be done whenever needed without additional user settings, which is very convenient. Let's see how we made it.
Here you can see our workflow. Totally, we designed 4 different experiments. First, let's talk about our dataset. The public dataset is from a public data challenge in 2002. It gives us ECG peak-to-peak intervals. The private dataset are provided by iCare Limited Company. It includes both ECG and PPG 5 minutes data from 10 different objects. However, all the raw signals have severe noise. Therefore, we first apply Butterworth's bandpass filter to process the PPG signal. Then, we design peak finding algorithm and the specific rules to obtain filtered peak-peak intervals. Finally, we calculate 2 non-linear, 3 time domain, and 3 frequency domain HRV features from peak-peak intervals, and 4 spatial features from the whole filtered PPG waveform. The first experiment compares public dataset ECG HRV with private dataset ECG HRV. The purpose is to get a ground truth and prove the reliability of the private dataset. We first manually select HRV features so that we can get a better understanding which features are more useful. The selected HRV features are mean heart rate, RMSSD, and SD1. Then we use naive Bayes for public dataset time sample selection. After that, we use LDA to reduce the number of features and do tenfold cross-validation using random forest classifier. The classifier accuracy shows that our private ECG dataset is reliable. The second experiment compared ECG HRV classification ability with PPGs. The results indicate that the wrist-based PPG is as promising as ECG signal. The third experiment compared PPG HRV classification ability with PPG spatial features. The results show that PPG spatial features have very promising classifier accuracy.
The fourth experiment focused on long short-term memory classification ability based on RR interval and spatial sequence. Here's the framework of LSTM. We designed 2 LSTM layers and 1 dense layer. For the 2 LSTM layers, we added dropout, used regularization to prevent overfitting. For optimizer, we have computer store check state gradient, atom and unatom, and finally choose an atom with a scheduled learning rate decay.
This image is the learning curve. The highest test accuracy is 75% received by spatial features. This result illustrates that the 4 spatial features are rarely promising. Since now we just have 5 minutes data for each person, we believe LSTM would do a better job if more dataset is provided.
To sum up, our approach could protect users' privacy and do person identification whenever needed. We proved that wrist-based PPG is as promising as ECG signal in smartwatch person identification. And based on experiments, we highly recommend 3 HRV features and 4 spatial features, and believe LSTM is promising with more dataset.